I occasionally teach a rather unorthodox class at the University of Chicago. We call it Philosophical Problems in Cosmology. And I love it because it gives me an excuse to put on kind of a different hat. Instead of playing, scientist, I get to play armchair philosopher for a quarter. So I was thinking, why don't we turn that course, or at least some of the highlights of that course, into a few episodes of Why This Universe?
I'm very excited for that. I'm very interested in philosophy of science, philosophy of physics, especially. I think this will be a really interesting series and I hope everyone finds it interesting. Yeah.
Yeah. And if you're not into this thing, well, you can listen to other episodes, but this one is going to be about philosophy of science. And I think we'll start where kind of the whole Western philosophical tradition starts. We'll go back to ancient Greece and talk about how those people thought about astronomy and about their universe. And we'll go from there.
If you enjoy the kind of conversations we have here on Why This Universe, then there's another University of Chicago podcast network show that you should check out. It's called The Pie. Join host Tess Vigland as she talks with leading economists about their cutting-edge research and key events of the day. Hear how the economic pie is at the heart of issues like the aftermath of a global pandemic, jobs, energy policy, and much more. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper.
So we may need to start this episode off with a bit of a disclaimer. We're starting our story of the philosophy of cosmology in ancient Greece, but the Greeks weren't the first people on Earth to do astronomy.
The Greeks were not the first people to study the motion of the stars and planets, or even the first people to apply mathematics to problems of astronomy. There are records of people in ancient Egypt, Babylon, Mesopotamia, all studying these sorts of things. And they did it for a bunch of different reasons. So if you go back and read their, fragments of those writings, astronomy is oftentimes deeply woven into their practice of religion. They used it for things like making calendars, navigating either on sea or land, and for the practice of astrology, which was very common throughout the ancient world. And it seemed to be something that kind of once you built up a sufficiently specialized, concentrated level of social interactions and institutions, people just started doing astronomy. We kind of see that throughout human history.
And it makes sense, right? It's like you look up at the sky at night and you see all these dots and you see that the Earth is powered by this strange light in the sky and all these things. Like, how could you not?
As somebody who's a professional astrophysicist, it's easy for me to say, of course people would do this. I've done it in, the modern era. But apparently it's something that, pretty much without exception, big groups of human beings with the resources they need to do this decide to do this. It's something about human nature, I think. So I could talk about the ancient Egyptians or Babylonians or whatever, but I'm going to talk about the Greeks. The ancient Greeks were the first, at least the first recorded examples we have of people who started to do astronomy in a way that looks naturalistic. I'm not going to say it looks modern. It doesn't look scientific, but they're the first people who would talk about how the universe might work without making direct references to supernatural things. Sure, they named all the planets and things after gods and whatever, but the people we're going to talk about today, when they decided to write their treatise on how stellar objects moved or celestial objects moved or whatever, they didn't refer to supernatural causes. And to me, that is like a step, not a big step, but a step, or maybe it's even a big step in the direction of something we would one day recognize as science, even if they're definitely proto or pre-scientific.
So let's get into the natural philosophers of ancient Greece that paved the way towards Western science.
So let's start with this figure, Thales of Miletus. Miletus is actually in modern-day Turkey, but it was very much part of the Greek world at his time. It's kind of like a colony of Greece, as I understand. So he lived in the 6th century BCE, almost 3,000 years ago. And Thales is called by a lot of people to be the first scientist. we don't have any records of anything he wrote down. So there's a lot of legend and mythology and history kind of all woven together when we talk about this guy, but he's oftentimes accredited with being able to successfully predict an eclipse that took place in 585 BCE. That probably didn't happen. I don't think it's realistic that they had, the kind of observations and the kind of quality of a model to like predict the day of an eclipse. But all that being said, it speaks to when people looked back on Thales hundreds of years later, they thought of this guy who was trying to make predictions about how things move in the sky based on his understanding of the universe and its shape and function and form. So maybe his accomplishments got exaggerated, but he seemed to be an early practitioner of something we'd call proto-scientific astronomy. Thales also made a lot of contributions to kind of early forms of geometry. He had some positions which seem pretty wrong now, but also kind of represent early attempts to answer questions about the world. Like, he seems to have thought that all forms of matter were different forms of water. And, if you look at water and its ability to freeze and become ice, like, I can see how that idea might start. But if everything is made of different forms of water, then isn't everything made of different forms of air or fire or whatever else you want to? You just called it water. So I don't know. I would like to have that discussion with Thales. I'm not sure what he meant. And as far as his cosmology model goes, he argued that the Earth had to be some sort of big flat disk that was floating in a giant expanse of liquid water. He also thought that the stars were giant burning balls of dirt. Okay, so like not stuff that we would call correct. Okay, the conclusions themselves aren't accurate depictions of our universe.
We don't necessarily look up to Thales because of his successes, but rather because he was one of the first people we know of who tried to answer questions about the world without any appeal to supernatural forces or characters.
When asking about why the world is the way it is, Thales didn't make any references to gods or any miracles, at least in the records we have. And he didn't seem to anthropomorphize natural phenomena. The earthquake didn't happen because someone was angry. He had a naturalistic outlook on this stuff. And that naturalism sets him apart from the earlier examples of people we have records of their thinking at that time. All right, let's move a little farther forward, moving away from Thales to Pythagoras. You probably know Pythagoras from his famous theorem. Of course, we don't really know that Pythagoras, had that theorem or originated with him or his followers, but somehow that name got attributed to it.
Oh, really? I didn't know that.
Yeah, we don't have any written records from this guy. So, we know that this guy was really into numerology and math, and he made important contributions, or his followers made important contributions to math. So it's plausible they had, the Pythagorean theorem or something like it. As a little sidebar, we always talk about the Pythagorean theorem as a squared plus b squared equals c squared, the sides of triangles and things. But algebra wouldn't be invented until the Islamic era, more than 1,000 years later.
So it's likely that they would have talked about something like the Pythagorean theorem without the use of variables like a, b, and c to describe the lengths of triangles and their relationships, but rather just sticking completely to geometry and shapes. So you can imagine if you start with a right triangle, like the Pythagorean theorem describes, and instead of assigning each side of the triangle a variable like a, b, or c, you just take each side of the triangle and literally square it, turn the side into the side of a square, and then compare the areas of the squares that you make based on each side of the triangle. Then if you add up the areas of the two squares you made from the shorter sides of the triangle, it'll equal the area of the square made with the hypotenuse. So no algebra here, just shapes, but you can get to the same ideas, so you can still make progress this way.
Pythagoras and his followers thought the universe was fundamentally made up of numbers, so kind of a esoteric numerological view of the world. He kind of looked at the world and saw evidence of mathematics everywhere. What I think he really saw, looking back on it with the benefit of hindsight, is a universe that was like, had order and logic to it. And math is one way of like expressing logic and regularities. But all the same, he thought of it in terms of numbers. Like Thales, Pythagoras and his followers had expressed a variety of views about astronomy. They again thought there was like an Earth that was shaped as like a flat disk. But unlike Thales, it wasn't floating in water. It was out in, kind of something like space. And there was an Earth, moon, sun, and 5 planets that were all revolving around some central point that he called the central fire. But because the Earth disk is facing outward, the inhabited side, I should say, is facing outward, we could never see the central fire. So you'd have to go to the opposite side of the disk to see it. So he's imagining a point in space with the central fire. We can't ever see it, but it's there.
So, I mean, this is sounding a little bit like hell, right?
How so?
Like, we're saying it's under the Earth, kind of.
Okay, good.
And it's this, like, ball of fire, this fiery world below us.
Yeah, okay, that's good. So I didn't think of it that way. I just pictured, like, the disk, the Pythagorean disk that he called Earth, like, floating out in space and just, like, in orbits around this point, kind of like we orbit the sun. But I guess if you, like, yeah, sure, in a pre-modern version of hell at the center of the Earth, sure. And then, in addition to all those things you can see and the central fire, the Pythagoreans also introduced another object called the counter-Earth, or at least it became known that later. I don't really know what this thing was, but it was kind of opposite to the Earth relative to the central fire. So, like, in the opposite side of the central fire, there was this counter-Earth. Why they added that is pretty esoteric. We don't have any writings from the Pythagoreans, but Aristotle wrote hundreds of years later that this had been motivated by the fact that the Pythagoreans thought 10 was a perfect number, but if you added up all the objects in their cosmology, there were only 9. So the Earth, Sun, Moon, and 5 planets, and then one body of fixed stars, all the faint stars, added up to 9, but they thought it should be 10. So they added the 10th object, the counter-Earth. And apparently 10 is considered to be a perfect number by the Pythagoreans because 1 plus 2 plus 3 plus 4 equals 10. Now, why that makes it more perfect or more likely to be manifested in nature is beyond me, but that's what they said.
What about 5?
Yeah.
And 15. And
so maybe they thought 15 and 21 and, et cetera were perfect numbers too. I don't know. But for some reason, they thought it couldn't be 9. In some ways, perhaps just coincidentally, the Pythagorean way of thinking about astronomy or the model had some modern features. The Earth was moving, okay, which was later going to be a very unpopular idea. It wouldn't really be until Copernicus that a moving Earth would become like mainstream astronomical thought. But unlike the more correct modern model, the Pythagorean model had the Earth in like a daily orbit around the central fire, rather than an annual orbit around the sun. Also, there wasn't any like revolution on its axis. That wasn't part of the story yet. So, they had some features that we'd recognize and others that would be very, very foreign.
So far, everyone we've talked about, we don't actually have direct written records of. So now we'll move on to the first person that we actually do have written records of, and it's a name you probably heard before, Plato.
Moving beyond the Pythagoreans to like the 4th century BCE now, Plato lived in Athens. He was a student of the famous philosopher Socrates. And unlike the others we've been talking about, Plato's entire body of writings are thought to have survived. Like he wrote a ton of stuff, and best we can tell, we have, copies of that collection of work today. So we know a lot more about Plato and his ideas than we do about the other thinkers that preceded him, or even the ones that followed for the most part. Plato put a huge emphasis on what he called forms, okay? Forms were like perfect idyllic expressions of things. So like he would imagine things like the perfect mathematical sphere or triangle or something, and he would see like imperfect kind of copies of those things in the real world. So we imagine there was like a perfect realm of forms in an imperfect physical realm. And this sort of dichotomy of forms and physical, like kind of suffused his whole, philosophy, his whole ontology or whole idea of how the universe was structured.
For example, you can imagine a perfect circle, and you can even conjecture about them with math and learn true facts about perfect circles. But if you look around, you'll never really find one in nature, at least not a perfect circle, right?
But he would say you'd see a lot of things in nature that are approximations of the true form of a circle. And he thinks that there's something deep to that. He thinks that nature is like pulled in the direction, this is my words, not his, but kind of pulled in the direction of these perfect forms, even if they never quite reach them all the way. So he thinks pure thought, mathematical thought or whatever about forms is actually deep down more true than like what we would call like observing the universe and learning about it through empiricism.
Another example of this is that you can think of something like the idea of a tree. So you know what a tree is, and maybe if you try to imagine the most general idea of a tree, you'll think of something that we call the Platonic ideal. So the essence of what makes something a tree. But you can't actually find the single most tree-like tree in nature, right? So the Platonic ideal of a tree is purely abstract. It doesn't really exist in nature.
Absolutely. And he talked about things like tables, the Platonic ideal of a table, and all sorts of objects like this. Yeah. The idea of the object, and then in contrast, the actual thing that exists. Of course, he thinks these ideas exist, and he thinks they exist in a deep and profound way, just in a different way than, the table that I'm sitting at right now.
Okay, so how do these ideas of perfect forms come into play in Plato's ideas about astronomy?
Plato really thought that astronomical bodies had to move in perfect circles, circular orbits, and he thought they had to move in like uniform rates. So he didn't think they could speed up or slow down. So he built a model of the universe where the Earth was a sphere and stationary at the center of the universe. And then the sun and the moon and the 5 planets. I keep talking about the 5 planets, but that was the 5 that we knew about at the time. Of course, there are more than that, but there were 5 that you can see with the naked eye. So the sun and the moon and the 5 known planets all moved around the Earth in circular uniform orbits. If you tried to use this model to make predictions, it wouldn't work very well. And I think Plato and his contemporaries knew that. He knew it didn't agree with data. And you would not take this model and try to make a good calendar with it, okay? Or try to navigate the seas with it or something. But that seemed to be not his goal. He thought that, making observations of the world would fundamentally be misleading or deceptive, or at least could be. So he was more concerned with the ideal, the mathematical perfection of the universe. So he insisted on these ideas, even knowing they led to predictions that didn't match observations. I would say that by modern scientific standards, this is like an extremely unscientific way to approach the world. But at the same time, we kind of do it all the time now. All the time, I'm finding myself writing down simplified toy models to describe things. And I don't think deep down they're right, but I use them because they're useful in certain contexts.
So when you say toy models, just to clarify, you mean writing down something that you know is oversimplified. It's kind of like the spherical cow thing. All cows are approximated to be spheres in some example, In
some Platonic ideal, all cows are spherical, right? Yeah.
Just because that's easier to work with and you can learn about that simplified model and then use that to extract some insight onto our much more complex real world.
And in Plato's case, he seems to have taken it farther, though. He didn't merely say this is a useful approximation that we can derive some truth from. He seemed to not be concerned with the fact that when we looked at the universe, it didn't match his model. He thought his model was more true than something that was he thinks the Platonic ideal of a table is more real than the actual table sitting in front of me right now, in some sense, or at least, I don't think I'm putting wrong words in his mouth, but something like that expresses his view. All right, so right around the same time was a different astronomer or philosopher, natural philosopher named Eudoxus. He lived at the same time as Plato. He probably, knew Plato and interacted with him and all that. And he took Plato's ideas and added some features. So whereas Plato's planets, including the sun and moon, moved in circular orbits through space, Eudoxus introduced big celestial spheres. So think of big round hollow shells that the Earth is at the center of, and those spheres carried the planets as they rotated with perfect uniform velocity in different directions. So now the cosmos was a series of these spheres. And Eudoxus seemed to be more concerned than Plato was about matching observations, so he added another feature. For each sphere, he added a kind of nested sphere, which rotated as the larger sphere rotated. So if you were to look up in the night sky and look at how a planet would move across it, instead of just moving uniformly across the sky, it could kind of move in a spiral. And that kind of freedom that you built into the model, these nested spheres, allowed you to get closer to matching the data. We call these things epicycles now. This is sort of nested sphere picture as an epicycle. And if, you weren't happy with your ability to match the data, an advantage of this model is you could always add another epicycle or another and another and another. It can't do exactly anything, but you can definitely get a lot closer to matching a set of data by doing this. And Eudoxus was very interesting in the sense that I don't think he thought his spheres were physically real. He thought these were useful mathematical constructs, which again, modern scientists do this all the time. We write down useful mathematical expressions that kind of fit the data without really thinking deep down the stuff we're writing down exists, but rather it's kind of a placeholder for the stuff we don't understand. So I think Eudoxus had a similar view. He's like, I can make a really good calendar and I can tell people how to navigate their ships well if I do this. That seems pretty useful. But yeah, all these celestial spheres and nested spheres, all that's probably not deep down what's out there in the universe.
If you wanted to, you could make the case that really this is what every model from science is doing. Do they describe reality, or do they just give us useful tools for interacting with nature?
Now, most scientists don't think this way. If you ask most scientists if they think, electrons are real, they'll say, of course they are. We've done this, long list of experiments and we can tell they're real. I'm of the view that science doesn't really get you to reality all the way, It gets you to descriptions of nature that, if you apply them, allow you to manipulate nature very effectively and make good predictions for how things will appear in different experiments and things. The example I like to give along these lines is, when Isaac Newton puts forth his theory of gravity, which, describes different objects pulling towards each other through this force of gravity. That's a very good scientific theory. It was extremely successful. It worked for a long time without any problems. We still teach it today and we still use it today. But when Einstein came along with his general theory of relativity, he showed there wasn't a force of gravity. The main central feature of Newtonian gravity doesn't exist at all. It doesn't mean it's a bad theory, but it just means that, when we talked about Newtonian gravity, that was really just kind of a useful placeholder for the curvature of space and time that Einstein would teach us about later. And maybe 100 years from now, someone will come up with a new theory that shows that Einstein's theory wasn't deep down right, and something else is really going on. And Einstein's theory will still be useful, but it won't be all the way down truth.
Let's move on now from Plato onto the next famous philosopher in the famous queue, Aristotle.
So again, 4th century BCE, he was born into some rather privileged circumstances. He was the son of the physician to the king of Macedonia at the time. And that king would turn out to be the grandfather of Alexander the Great. Aristotle studied at Plato's Academy in Athens for 20 years, I think. And then he became the tutor to the young Alexander the Great. So talk about proximity to greatness, 20 years around Plato, then you become the tutor to the greatest military mind of ancient history. And then in 335 BCE, he went back to Athens and established his own school there. And over the course of his career, Aristotle wrote books or treatises on basically everything philosophers were talking about at the time, about 150 different, pieces of writing, but only about 30 of them survive. So unlike Plato, a lot of Aristotle's stuff we lost, but still we have quite a bit in terms of what he wrote at the time. So Aristotle learned a lot from his teacher Plato, but he placed different emphases on things. Unlike Plato, Aristotle thought you could learn things about the world by observing them. He trusted empiricism more, but he didn't like to do experiments. Basically, he would I'll sit back and I'll look at that thing and I'll look at it and learn about the universe that way. But once I start intervening and constructing controlled experiments, well, then I'm artificially changing, I'm fixing the results in some way. And he didn't think that was a good way at truth. And that was actually a big problem for, the next 1500 years, people pushing back against that and saying, no, you can trust this. But that was his view at the time. But still, he was much more empirical than Plato. Another thing that set him apart is Aristotle's view of nature was deeply suffused with teleology. And teleology just means the premise that an object's purpose determines its behavior. So, for example, Aristotle thought that the element Earth, is supposed to be, its purpose is to be at the center of the universe. So if I have a big empty universe and I have a chunk of Earth and I let it go, it's going to start moving towards wherever the center of the universe is. So I was really confused about this element of Aristotle for a long time, and it just shows that once you learn certain modern ideas about science, it's really hard to unlearn them sometimes. But I always imagined that for Aristotle, the center of the universe was coincident with the Earth because the Earth defined where the center of the universe is. Kind of like the center of the sun approximately defines where the center of the solar system is. But he did not mean that. He meant there was a place, and if you took all the stuff out of it, there would still be that place where the Earth wants to move to. And the Earth is there because it's the center of the universe. It's not that the center of the universe is where the center of the Earth is. The arrow of explanation goes in the opposite direction.
So to get your head around this distinction, I guess you could see, for example, the Earth moving towards the center of the universe. You could explain that either by there being some force that the universe exerts on the Earth that pulls it towards it, or it could just be the kind of will of the Earth that causes it to just move towards the center.
Yeah, and I don't think Aristotle had any notion of force. He just thinks things do.
It's more like drive.
Yeah, drive. That's a good word. Yeah, I think a big part of the reason why Aristotle developed this view is he'd spent a lot of his formative, years studying biology. And if you look at animals and plants and their biological systems, at least if you don't know about Darwinian evolution, they really do seem to do things because they have some purpose. They eat because they're hungry and they need energy, or they have wings that allow them to fly. The purpose of wings is flight. And he didn't know anything about Darwinian evolution, so he couldn't think about it in those terms. And then I think he carried over those notions by observing biological systems and saying the universe as a whole has elements with purpose. And he pursued, a cosmological model that had that built into it.
That kind of makes sense. I mean, you do, without understanding evolution, you look at, an anteater's nose and you're like, okay, the anteater must go and get ants out of the tree because that's what it, that's what it's meant to do.
All right, so let me tell you Aristotle's view of the cosmos, his cosmological model. So, like Plato, he put the Earth at rest in the center of the universe. And then, again, like Plato, he only allowed for perfect circular and uniform motion. Those were the only kinds of motion he thought could be permitted in the cosmos. He also had the spheres that the planets were carried by, like Eudoxus had introduced. But whereas Eudoxus thought that these were like useful mathematical fictions or tools or something, Aristotle seems to have thought they were real physical objects. They later became known as the crystalline spheres. So he pictured planets being carried on real physical objects or rotating in perfect circles. Like he really thought that the kind of terrestrial realm where we live on the surface of the earth, basically everything out to the atmosphere of the earth or something, was fundamentally different than all that stuff out there in the cosmos. So on Earth here, we have air, fire, earth, and water that make up everything. We have all sorts of volatility and change and kind of imperfection and all this stuff. And then you got out and beyond that realm. And first of all, stuff was made of different materials, stuff he called quintessence, a fifth element. And unlike air, fire, earth, and water, which lended itself to change and imperfections and whatever, quintessence in the celestial realm would, be unchanging and perfect and kind of like something like what Plato would recognize in his forms, some sort of idealized version of reality. And you might say like, well, obviously it's changing because planets are moving across the sky and stuff. But with this kind of perfect uniform circular motion, Aristotle pictured something that was like a constantly moving clock. Okay. Like almost like gears and stuff. Like, sure, like it is, things are moving, but without anything really changing. Things can kind of stay in this state of motion forever. And, he thought all the spheres out there were perfect spheres. He didn't think they had any blemishes. He didn't think, et cetera, et cetera, et cetera.
They wouldn't like break or decay or like something wouldn't slip off and wreak havoc. All
that. Yep. That's right. That's right. So a couple of other things that Aristotle thought that were kind of related to this. He thought the universe had to be eternal in time. He said, since there can't be change, the possibility of something having a beginning, wasn't a possibility. So he thought the universe had to exist for a long, long time. This would actually be a problem when Christians, theologians tried to incorporate Aristotle's ideas more than 1,000 years later with a biblical idea of creation was incompatible with that. He also thought that the idea of empty space or a void or vacuum or something was logically impossible. He incorrectly inferred that if you had empty space, everything would move at an infinite velocity through it. He thought the only reason things didn't move at infinite velocity was the medium slowing them down or something like this. So his physics was just all kind of wrong. But like that led him to think that all that space out there had to be filled with this quintessence. You couldn't just have empty space. Aristotle's theory would be super, super influential later. It didn't make for good predictions, kind of like Plato's didn't. But it established how kind of natural philosophers thought about our cosmos for a very long time.
So aside from Plato and Aristotle, the big names, there were also other people at this time period who got surprisingly close to being right about a few things. These ideas didn't necessarily take off at this time, but it's interesting to look back and see who got things right ahead of their time.
Heraclitus suggested in that time that the Earth rotates on its axis. Okay. So this simplifies things a lot because if you look up in the night sky, everything kind of moves more or less together across the sky. And if you're having all those spheres moving or whatever, well, it's kind of a coincidence that they're all kind of moving roughly together and things like this. If you just have the Earth spinning on its axis, a lot of that work's done for you. Of course, there's an obvious objection to this, which is it sure doesn't feel like we're spinning super fast, right? For that to be true, we're like moving at like 1,000 miles an hour all the time. I know what it's like to move on a horse at 20 miles an hour or something, and you notice that. So this would be really easy to notice, you'd think. And really what this means is that people didn't have good conceptions of things like momentum and stuff yet. So they couldn't answer these questions. So people would object to Heraclitus's picture of a revolving Earth on these sorts of grounds. It wouldn't be until after like Copernicus and Galileo and stuff that became popular as an idea. Also in the 4th century BCE was Aristarchus, and he proposed a heliocentric model, so a sun-centered model of the solar system. There wasn't really any observational evidence one way or the other then. And one problem with this hypothesis is if it's true, then you should be able to notice this thing called parallax, which is like the stars moving a little bit in the sky, either by day or by season or something like this. And nobody noticed that. So the fact that there wasn't any observable parallax meant that either the Earth was stationary or that the stars were just really, really far away, much farther away than anything else. Of course, the latter is what's true. But at the time, that just kind of seemed like an implausible amount of distance. It seemed like ridiculously far away. So Aristarchus's idea wasn't popular for that reason. These were ideas that would eventually be rediscovered and like look a lot like a modern solar system, but they came at too early in history the right time hadn't come yet.
Yeah, that's an interesting way to think about it. Like 4th century BCE, that's a very long time ago. That the idea that we might not be ready for the right idea.
Yeah, I mean, if you teleported me back in time to the 4th century BCE and, I knew the language and whatever, and you asked me to try to convince these guys that, the sun was at the center of the universe, I don't know that it would go well because I wouldn't be able to point to evidence that would really convince them. For example. Okay, so I have one more name I want to talk about on this episode, and that's Claudius Ptolemy, Ptolemy. So this is much later. So I'm jumping now from the true ancient Greece to the kind of late Hellenistic periods, like 150 or so AD, not BCE anymore. So this was a scholar who was affiliated with the Museum of Alexandria, and he kind of lived and worked in a different period of history as far as astronomy goes. Those ideas we've talked about on the show had all remained in place, but astronomy had gotten more quantitative. The measurements had gotten better. But like I said, they still hung on to these old ideas of circular uniform motion with a stationary Earth at the middle of the picture. And to make better predictions, astronomers, including Ptolemy, had added a lot of epicycles to their theories, those nested spheres, okay? And then they had added a bunch of other features too. So they added something called an equant. Okay. So basically, whereas Plato said everything had to move at a constant speed around its circle, if an equant is basically the idea that the object's going to move in constant amounts of angle around the circle, but relative to a point that's not at the middle of the circle. So I draw a circle, I displace the center, and relative to that angle that is going to sweep out at the same amount of angle all the time. And what this really does is it means that along part of the circle, the object moves faster, and on the other side, it moves slower. So that gives you more flexibility in your model. And they also added something called an eccentric. This is basically just allowing those spheres to not be perfectly centered on the Earth. They could be a little bit off-centered, again, giving your model more flexibility. And when you put in enough epicycles, enough eccentrics, and enough equants, you can get pretty close to describing the observed motion of the planets and sun and moon and stars, all that stuff. And basically this meant you could write a really good calendar. You could navigate really well. All the things you want to use astronomy for on practical grounds, you could do with the kind of models mathematical astronomers like Ptolemy were developing. By this point in time, astronomers had become fully committed to what people call saving the phenomena. So the idea here is you believe in these philosophical principles of things like perfect circular motion, and naively, those don't match what you observe. The phenomena is not described. So you bend over backwards, you tie yourself in knots, you go into contortions, all to save your principles when they come up against the observed phenomena. So they could take perfect circular motion as defined in that era and hold it against the observations and do pretty well. Again, they didn't have great data back then. There were no telescopes or anything, but the data of the time could be accommodated with these very complicated, very difficult to construct and calculate with theories or models.
Were there actually no telescopes yet?
Yeah. It wouldn't be until Galileo's time, early 1600s.
Not even a simple mirror.
No.
Wow.
Yeah, just months before Galileo used his telescope in 8, maybe 1609 or something. That's when the telescopes were invented for the first time.
Okay, wow. So they were doing all of this stuff in the epicycles just by eye.
Yeah. This is all naked eye astronomy. That's right. So you can see why it's hard to make the kind of progress you'd need to make. So the astronomers, which were what they called the mathematicians doing this sort of work, were fully on board with this Saving the Phenomena program, and they would be for like another 1,000 years.
Did they also call it that, or is that your phrasing?
I think it's a translation. Okay. I mean, obviously it's not English, but I don't think they meant it to be derisive. I think Saving the Phenomena is definitely like the phrase that you find in all the books now. That's what they were trying to do, and they did it very well. They went to great lengths to make models using perfect circular motion that could accommodate the data, and that's no easy task. But then there was a second group who weren't concerned with math. They're more like what Plato and Aristotle looked like. They had principles. They thought, they could deduce from like logical foundations what the universe would be like. And these became known as the natural philosophers, distinguishing themselves from the astronomers, who were the mathematical ones. And this, kind of separation of domains would persist well into the Middle Ages, and it really wouldn't be until the beginning of, well, at least the Renaissance and then the following scientific revolutions that took place in Europe and Western Europe that would kind of break that dichotomy. And but for 1,500, 1,300 years, something like that, this kind of division of labor and two different worldviews about how to approach things would be pretty harshly maintained.
So that's all for today's episode of Ancient Greek Astronomy, but stick around because in the next few episodes, as Dan goes through his course, we'll be making more episodes about philosophical questions in cosmology, and they'll get much more modern. So if this wasn't your cup of tea, hopefully the next episode will be. Why This Universe is brought to you by the University of Chicago Podcast Network. It's edited and produced by me, Shalma Wegsman, and my co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. If you like our show and you want to support us even more, you can find us on Patreon. There you can access ad-free episodes of the show, as well as exclusive Ask Us Anything episodes where you get to ask Dan and I direct questions about physics or anything else. So if you are curious about that, you can find it at patreon.com/whythisuniverse. Thank you so much for listening and for your support.